So, let us continue to talk for a few more minutes regarding the layouts of various plants and the facilities uh, that we have in the country. As I have pointed out already, that we have a very strong secondary steel producer as well as primary steel producers. We have both integrated and mini mills, and mini steel plants we have basically induction furnace based and arc furnace based. Arc furnace based facilities, which are basically DRI oriented or DRI based, they have both come up in the Western India, because you know that we have gas based DRI production units as well as coal based DRI production units. You have Midrex process, which is a gas based process. Then we have SRRN or rotary kiln process, which is a coal based process. So, mostly in Eastern India we have coal based DRI units, a good number of DRI plants with not much infrastructure. They are just money making units actually, nothing beyond that. Gross violation of environmental norms, these have come up in the eastern coast. On the other hand, we have the gas fired or gas based DRI processes, mostly located in the Western India because of the availability of natural gas there. It is also understood, as I have pointed out, that if India has to grow, India has to develop, it will need steel, and perhaps from that point of view 180 million ton by 2020 is not too massive a figure. And it is also certain that because of the logistic problems, because of less capital inflow, because of problems with land acquisition, infrastructure, etc., perhaps we will witness in the years to come, more or less similar rate of growth in the primary as well as in the among the primary, between the primary and the secondary steel producers. So, we will see parallel growth of the integrated steel mills as well as mini mills in the country. And of late, many steel plants are being launched, which has a capacity between 1 million ton to 2 million tons. Balaji Group, then Swayam Group, Bhushan Groups. Bhushan Group is also expanding, and there are umpteen number of steel plants which are planned to be coming up in the eastern coast, particularly in Orissa, Jharkhand, and Chhattisgarh area. Now, having said so, we understand that the primary steel producers in this country, they are going to be using mostly LD steel making process. They, in the future developments, we may see integrated mills coming up with thin slab casting or maybe strip casting. It is not yet certain, because strip casting is now a proven technology, and I heard that SR Steel is already negotiating with Nucor, which is one of the pioneers in strip casting technology, for setting up of plants. And today, I think I have mentioned during the course of this course that we have continuous strip production technology, which is economically and energetically extremely efficient. So, newer technologies we will gradually see getting into the Indian market as well. Subtle variations do exist, as I have mentioned yesterday regarding the steel making technology. Subtle variations also exist in terms of ladle size, stun dish capacity, nature of products, nature of secondary treatment, types of vacuum degassing treatment. Some plants use tank degassing techniques, some plants use circulation degassing techniques. So, although the subtle variations are there, the process route more or less is same in all integrated steel plants, and in the foreseeable future, I do not think it is going to change by and large. So, we will have a primary steel making followed by lucid secondary steel making, but the emphasis on secondary steel making is going to grow more and more in the years to come as we put in more and more stringent requirement on the quality of steel. And finally, we have casting technology. Ingot casting has also been completely phased out. Sale, of course, will not be growing. We have to see what happens to the SAIL plants in the year to come, with national orientation changing a little bit, and we are thinking more in terms of these investments. Maybe some of the SAIL plants may go out of the SAIL umbrella in the years, and that we have to really watch. But at this moment, at least no new SAIL plants, no new RINL ventures are likely in the horizon. It is mostly the private sectors, Jindals, Mittals, the Ruyas of the SR group, etc. They are actually planning to set up more and more integrated steel mills. But so far as mini steel plants are concerned, there are so many groups. MESCO is another group which is trying to expand. So, so these are not so famous industrial houses, but we will see such ventures coming up all over India, South India, Eastern India, but maybe primarily, it is the developments are going to be taking place either in the Western India because of the availability of cheap fuel, or in the Eastern India where we have abundant low grade coal available to us. Now, if we have to get to the figure of 180 million ton by 2020 from 55 million ton 2009, we have to see that is it sort of a daydreaming, is it, or is it possible for us to achieve? And in view of that, I think we have to now understand that the GDP is very high, so maybe we are in a position, provided government makes land available, the market can generate a lot of cash, and we should be in a position to gear up our steel making facilities. But the issue comes now that what are the problems? That we need to understand. So the problems, this journey is not going to be so easy, despite the growing economy, despite the demand for a large amount of steel. I do not think it is going to be an easy journey, because we have a lot of problems, and I envisage the problems, or I tend to list the problems. One is our raw material problem. Another is our operational problem. Yesterday, I have tried to briefly, in the last lecture, I have tried to briefly mention that we have an excellent iron ore, and the amount of reserve is also pretty good, and we have good amount of coke also, but our coke is laced with large amount of coke ash, 22, 25, 28%. And what is coke ash? The coke ash basically is silica, alumina, etc., and it contains a lot of sulfur as well. So iron ore is basically, we have a lot of fixed iron is very good, one of the finest iron ore from that point of view, but at the same time our iron ore contains a lot of silica and alumina. We know that silica can be reduced in the blast furnace. So therefore, the tendency to produce a high silicon pig iron in Indian blast furnace is somewhat relatively high, and this tends to offset the good quality of iron ore. So some beneficiation seems to be, particularly when we will be talking about low grade processing of low grade iron ores, because not all grades of iron ores, the iron ore reserve is of 60 or 65% iron. So there are low grades iron also, and then the beneficiation of iron ore, particularly removing silica, etc., is going to be meaningful. So if you have more silica, in the relatively more silica, and you have 1:1 proportion roughly alumina, so the alumina will invariably go to the slag phase. So you are forced to use maintain a very high hearth temperature, and that high hearth temperature, what it does, it causes thermodynamically more favorable, creates more favorable condition for the production of high silicon pig iron. And this high silicon pig iron upsets the economics of steel making, as we all know, because high silicon pig iron means we have large amount of heat produced in LD converter, we have large volume of slag. If you have large volume of slag, then we have large amount of CO to be added. If you have large amount of heat which is evolved in the LD reactor, then the lining life is going to be drastically affected. So high silicon pig iron, it has problem, and alternatively, if you don't wish to take that to the LD converter, you have an external desiliconization that is again deterrent to the production of the steel, because of the simple fact that external desiliconization will consume some amount of time and slow down the pace of steel production. Ash, of course, is a issue of concern to all of us, and our coke rate in the blast furnace, if you go back, is also not quite encouraging. Okay, we are because the coke ash, the fixed amount, fixed carbon in coke is going to be less. More and more is the coke ash, and that's why our coke rate in our Indian blast furnaces ranges 700-800 kgs per ton of hot metal produced, because we are charging less fixed carbon and more ash possibly, which is reflected in the high figure of coke rate for blast furnaces, etc. And again, we are talking of more slag, more coke ash means the process more coke essentially implies that the process is environmentally less friendly. We are producing more greenhouse gases, and finally, it will have large amount of slag which will be produced, because silica, alumina which are present in coke ash needs to be flushed, and as a result of which you have a downstream problem of waste disposal. Okay, so these are some issues. So as we go on to 180 million tons, okay, so the waste generated are also going to be much more, and we have to see that when there is so much of crunch on the land, how do you really distribute or manage the waste which is generated out of the steel plant. Of more importance to me is the operational problems in the Indian steel plants. I mean, the technology in the Indian steel plant is very old, and particularly I have mentioned in the previous lecture that electric arc furnaces, if you go and taken place in the arena of steel technology, it is just unbelievable, uncountable. And if you go to the Indian steel plants, you will see that the technology has taken a back seat there, where the owners are more concerned with the number of heats, amount of liquid metal, without bothering much about the general safety, the energy efficiency, the cleanliness in the plant itself, and these have been issues. These are issues which have been totally ignored in the plants. So there are a lot of operational problems, and these operational problems, I think I will say that leads to we have number one is we can say that we have high. Or first one, I will say that age-old technology. I am not saying each and every plant in India uses old technology, but by and large my experience has been that for example, one simple last thing I am going to tell you is that if you visit Indian steel plants, most of the places you will see that ladles and tundish, they are operated with stopper rods, and in no steel plants, no modern steel plants, if you go and visit, for example, Japanese steel plant, Korean steel plant, POSCO, etc., nowhere you will find they are using stopper rod. Stopper rod, you remember, this is to regulate the flow out of the tundish, regulate the flow out of the ladle. Okay, so they are still persistently used in many Indian steel plants, but stopper rod technology has been phased out from, literally phased out from modern steel plants, where we are now using slide gate technology. Okay, so this is just one single example. Then we have, as a result of high age-old technology, we have lot of problems in the plant, and therefore we have and the layout of the plant is also not scientific. These have housekeeping is extremely poor. We have emission, recovery. These are big issues in Indian plants. We have high specific energy consumption. We have poor process control. These are all important issues. Layouts of the plant, for example, I have talked about a little bit about age-old technology. Layout of plants not scientific. Many of the steel plants you will see, because they are age-old, there is no synchronization of activities. For example, you will see that the furnace is here. The furnace is here, for example, and the material is tapped here in the ladle, and then it goes like this, and we have a LF station, and again the material is brought here. We have casting. So, there is lifting by cranes. So, sometimes they move on rail, sometimes they are lifted from one place to another place. So, if electric arc furnace, then it is tapped, it moves in one direction, and then it goes to the LF or VD station, then it moves in the reverse direction, because the plant is not scientifically laid out, and this creates a lot of logistic problems in running the operation very smoothly. So, and even if you look at the overall layout, the scrap yard is at one corner, the control room is, control rooms are not properly located, control equipments are not functioning properly, and these all creates a lot of problem in terms of managing the available resources very efficiently. The plant layouts are in general, except for few modern plants, and this I am more or less I'm talking about mostly the mini steel plants or the arc furnace based steel plants, okay, where it's an extremely primitive layout is there in the plant. And what happens is, for example, if layout is not scientific, in that case what happens is, for example, you try to process steel through this, and at one point of time you find that because of transportation etc. holding, your temperature has dropped to such a level that you require really reheating in the LF. So, you have to shuttle between LF time and again in order to bring the metal at the correct temperature in the continuous casting bay. Housekeeping, for example, is extremely important. Why? For example, in most of the steel plants, if you go, you will find that it is smoke, dust, the cleanliness level is very, very bad. Now, if the housekeeping is no good, in that case it is very difficult to attract new engineers and asking them to make their career in steel plants, because I have been visiting many steel plants, and I have been telling people that unless you are able to create a congenial atmosphere, unless the environment in your steel plant is good, no engineers from NIT and IIT are going to make a career in the Indian steel plants. So, this is extremely important. If you see outside steel plants, they are so clean. Many of you may have seen videos, okay, and there are few people, and of course, this brings me too many man hands. the workforce is too large in our steel plant. Okay. So, coming back to the housekeeping, we require, it should look like a modern steel plants. Modern steel plant, extremely clean, very little amount of gases and dusts or smokes, and you go to steel plants, you find scrap is everywhere, dirt is everywhere, broken pieces are everywhere, and you don't feel like working there at all. And if that is the scenario, in that case, this is going to cut a very sorry figure as far as new recruitments are concerned. And it projects, on the other hand, many people have, foreign countries have come, seen Indian steel plants, they have interacted with me on diverse fronts, and have told me Indian steel plants are 50 years behind in terms of all these things. Emission recovery. Emission is rampant emissions in Indian steel plants. If you go, you will see that they are all red powders everywhere. There is dust, and if you go to the ELAB station, you go to the electric furnace, during the furnace stepping, everywhere there is so much of smoke and dust that it becomes horribly difficult, to work efficiently under such conditions. And these are certain, we have extremely GCP, gas cleaning plants. Okay, many places, many times I have seen the gas cleaning plants which are essentially attached to the LD converter, electric furnace, level furnace, etc., are not at all functioning, and the dust, etc., from these furnaces are being released to the environment in a callous manner. Again, recovery of heat from the spent gases is also a very important issue which you have not been able to give sufficient attention. And all these things, layout of the plant, age-old technology, emission recovery, leads ultimately high specific energy consumption. Poor process control. In many of the plants I have seen that they don't have, for example, flow meters which can record the amount of the flow, oxygen going into the furnace itself, and as a result of which they tend to overblow oxygen. And if they overblow, in that case, the slag becomes more and more richer in iron oxide. Sometimes it is 25%, sometimes it is 35% with excessive amount of oxygen blown. And if 35% of your iron slag contains so much of iron oxide, in that case you can imagine what is going to happen to your yield. So therefore, process control, adequate process control is necessary. For that you will have to have sensors and gadgets. PLCs to be functioning all the time, they should be giving you good and reasonable results. And finally, we have too many hands. Of course, we are, we have to look at the society, but even China, which is a socialist country, the number of hands per ton of steel produced is far less than ours. In our steel plants, we just have too many people. The liability on the management is also high in terms of their healthcare cost, and other recurring costs, and as a result of which the profit really is not that much. Many of the steel plants, you see that they are in India, they make enormous amount of profit. It is because of one single fact, that it is not because of technology, it is not because of very efficient management, but it is because of one single fact, that they have captive mines, and from captive mines they are able to get the basic raw materials at an excessively cheap price. Okay, and that gives them the edge over others. So plants which are operating in India, there are many of them, I don't want to name them here. Okay, they have their captive mines, and from that captive mines they get raw materials at a very cheap rate, and as a result of which the final product they roll out is really extremely low priced, relatively low priced with respect to others. Now, having said so much, the other important issue is that what we have recently seen is an issue of manpower. So, raw material problem, operational problem, and then we have manpower problem. This is very important. And in this context, I wish to spend a few more minutes on the topic of steel education and research in India. Now, when you have so much of steel produced, so many new steel plants coming up, we will certainly require metallurgical engineers, particularly people having interest in steel making. We possibly will not be hiring graduates from Chinese to run our steel plants. So, we require qualified manpower, we require people who have a lot of interest in steel making. Now, we have as you are aware that we have a full-fledged Ministry of Steel and Mines that takes care or controls all steel related and mines related activities. We have a cabinet minister. We also have MHRD, which Ministry of Human Resource and Development, which looks after the overall higher education as well as education in this country. Now, recently under the aegis of the ministry, we have Indian Institute of Metals. This is not Indian Institute of Management, but Indian Institute of Metals. The headquarters is in Calcutta. So, with the intervention from MOS, IIM has constituted a committee, or Ministry of Steel asked IIM to constitute a committee to look into the issue of manpower shortage in steel plants. Remarkably speaking, I have seen that in 1 month, there is a unique example. I could locate one single person working in 3 different steel plants. He was first working in X, then after 20 days, I visited another plant and I found that the person has moved to the second, another steel plant Y, and then finally by the month end he has moved to another steel plant because he was getting more salary. There are not takers, and as a result of which what happens is it is the same person who goes from one plant to another plant, and at the grassroots level or at the graduate trainee level, we have not been able to recruit too many people for our steel plants because of the simple fact that we do not roll out that many engineers today who has requisite expertise and knowledge of steel making. And also on the part of the students, as you are aware that students do not show much interest to make a career in steel because it is not as attractive as nanomaterial, it is not as attractive as biomaterial, it is not as attractive as infotech, but maybe it is an age-old field, and also the plant conditions, etc., have been deterrent for the students to take up a position in the steel plant. So, we have although so much of proliferation of education has gone under the aegis of the Ministry of Human Resource and Development. We have so many deemed universities coming up, so many engineering institutions coming up. Remarkably speaking, there are very few, you can just count them in fingers. In the last 5 years, engineering universities or institutions have opened which have metallurgical engineering as a discipline. I think last 5 years, I remember there are one in Orissa, then NIT Bhopal has started a program in metallurgical and materials engineering. And also you may have noticed that earlier, while the education is basically metallurgy oriented, say 30-40 years back, today the orientation in most of the engineering colleges are materials oriented. Earlier we used to be taught metallurgical thermodynamics. Today the thermodynamics course is restructured as thermodynamics of materials, where more thrust is given to defect thermodynamics. Chemical thermodynamics, Gibbs-Duhem equation, Lingham diagram, etc., have possibly been kept aside to some extent. And as a steel maker, we would like to see that there is emphasis on chemical thermodynamics, there is emphasis on chemical thermodynamic softwares and so on, so that then the engineers can carry out small or relevant calculations on a daily basis. So, the curriculum has also gradually drifted towards the materials science. There have been new areas which are coming up, emerging areas, and thirdly, we have too few institutions catering to the needs of the metallurgical and materials engineering. And statistics is almost 1000 to 1200 metallurgical engineering graduates are produced in a country like ours. And although steel plants have lot of job openings, lot of vacancies, they do not find employable graduates at the end of the day. So these three problems, that too few metallurgical engineering graduates and passing out, and then we have metallurgical engineering curriculum which is lopsided, getting lopsided towards materials education, and also emerging areas. These three have really put a punch on steel makers' ability to recruit more and more people. So the task force now mostly comprises of BSc graduates, diploma holders who are given some training rather than BE metallurgy or graduates in metallurgical engineering, because that too many number of metallurgical engineering graduates willing to work in a steel plant are not simply available. So this is going to be a serious concern for us in the years to come, that we do not have too many engineers. And also here I would like to blame the steel plants also to some extent. They might recruit the metallurgical engineers, for example, but the environment in the steel plant in this country is unfortunately not that creative, because the graduate engineers, if he is recruited, we cannot expect him just to press a red button and a blue button, tap the heat and be content with it. So he has to apply his mind, and he needs a creative environment. And steel plants who only think in terms of number of hits a day, unfortunately has not been able to give that creative atmosphere to the new recruits. And as a result, young engineers going and working in the steel plants get really disillusioned because they don't find much creativity there. There is not much scope of improvement because the management does not nurture excellence. They just look at the quantum of steel that is being produced. So there are many issues. It is not just, it is a very complex problem. Ministry of Steel is there, MHRD is there. We should have by now, envisaging that, well, we will need steel by 2020, a lot of steel, and we should have been able to by now, reinforce our steel education and research program in the country, so that we have a smooth production. I mean, in most countries we have an iron and steel institute. Where is such an institute in this country? Okay, we do need now, maybe its time has come that we have a separate institute which will roll out people with requisite qualifications in iron and steel technology, who should be, in a position to take up the occupy the position of graduate engineers and so on. So despite a full-fledged Ministry of Steel, despite a Ministry of Human Resource and Development, what I see that steel education in this country has been ignored for quite some time, and today the number of graduates produced having interest in steel making, you see, this is a really perpetual problem, in the sense that when we were students, there are a lot of seats of excellence in extractive metallurgy in this country, or iron and steel technology, be it IISc Bangalore, be it IIT Kanpur, IIT Kharagpur, IIT Chennai, IIT Madras, IIT Bombay, and lot of NITs also. But today the number of experts, the number of professors involved in teaching and doing research in iron and steel has dwindled remarkably. You can ask that why it is so important, because when we have professors teaching and doing research in iron and steel, it is they who induce, create the interest among the students. Okay, it is they who supervise the graduate students, and these graduate students at later stages become leader in their field. So the professors have a proactive role here, and unfortunately, in the last 10 years or so, the number of professors doing research and teaching in steel making has reduced to an alarmingly low level. And my quote of the day is like that: the steel making professor has become like a panda. Panda is an animal, and I think World Wildlife Organization has declared it to be an endangered species. And I think a professor of steel maker in this country has also become an endangered species. And I think a very viable steel program, parallel to the material science program, is available only in Japan, which spends, there are a lot of universities where there is still research going on. There are people who takes a lot of interest in steel making, and at the same time, Japan is doing excellent in terms of, electronics and other exotic and advanced materials. But unfortunately, our vision has been sometimes somewhat distorted, and as a result of which, the education program has suffered tremendously, and I have been mentioning that it has its own problem now, which we are going to see or experience in the years to come. Research in iron and steel, for example, indigenous research in iron and steel is very, very poor. Although we have a full-fledged research, RDCS, this is under SAIL, has set up a huge research center, but we really have not been able to come up with a new technology. Many developmental works, yes, we have been able to do. We have been able to improve some of the existing processes, but not new technology. So, looked at from such point also, we do not have a sizable or a meaningful R&D activities in steel in the country. I think Chinese in that front are doing much greater, much better than us. A lot of Indian steel plants today, I go and see, they are buying, for example, Chinese technology. Chinese coke ovens are being installed in JSW. Pulverized coal injection in blast furnace, entirely Chinese technology. But where is the equivalent Indian technology? We have not been able to come up that, and I think we have faltered somewhere down the line, and that's why the scenario, although we have painted a rosy picture, but the scenario in terms of manpower, in terms of research, in terms of the general conditions of the plant really do not look that attractive. So, this is I think the last lecture of this course, and now I have come to an end, and I do not wish to go beyond this, but I think there is a lot of challenge. The last statement that I am going to make as far as the discussion is concerned is that we require very knowledgeable people now to contribute in the area of steel making. I have mentioned earlier also that the technology is 150 years old. It is near perfect technology. So, just by merely attending the shop floor or going on a daily basis, you will not be able to contribute. Your knowledge of the subject has to be very, very good. You have to be equipped with, modern subjects, modern tools, knowledge of computer, knowledge of fluid mechanics, knowledge of kinetics. All these are necessary, and then possibly we can see that, well, you can improve the casting rate further, you can improve the yield further. We are already talking about 92-94% of yield in steel plants. So, it's a near perfect technology that we are dealing, but in our country, the mindset has to change. The owners and the government has to change their mindset, and product, for example, steel products, they are completely dirty products that we today produce. And these products, and government is of course going to bring in some regulations. There is so much of inclusions that really you cannot apply them in strategic application. Today it is fine, but if you put inclusion laced steel, loaded steel for making bridges, you can imagine after 50 or 100 years down the time, down the road, what is going to happen to the fate of all these things. So these are very important issues, and as a budding steel making engineers, you should be concerned about it. My objective, as well as Professor Korea's objective in this course, is to expose you to the subject, give you a modern outlook, and bring you to a point where you should be able to think yourself, what are the ifs and buts, what is the subjects, what are the loopholes, what are the problems, what is the scope, and put everything in the perspective of India, because India has to grow, India has to develop, and India will need more steel. Thank you.